For the first 3 days last week, Tuesday, Wednesday, and Thursday, what we were looking at are called arithmetic sequences. And an arithmetic sequence is a pattern of numbers that is arithmetic in nature. And that word arithmetic in terms of mathematics means you're increasing by the same amount each time, or you're decreasing by the same amount each time. There's what we call a common difference. And you can determine any value of any term if you know the first term, which is T1, and the common difference, which is D. You can create a formula called the general term. And into that formula, you can put whatever n value you want. If you put n equals 12, then what that formula is going to calculate for you, with a little bit of help from you, is the value of the 12th term. What we learned on Friday is that when you start adding these terms together, we have this thing called Sn instead of Tn. And Sn is a way for you to add up all of the terms. So for example, if you are asked to determine S12, that's different than T12. T12 is the value of the term in the 12th place. S12 is the value of T1 plus T2 plus T3 plus T4 plus T5 plus T6 plus T7 plus T8 plus T9 plus T10 plus T11 plus T12. It's the sum of all of those terms. And there were two formulas that we learned about. The one thing that is not really obvious in these two bottom equations, I mean, I think it's pretty clear n is how many terms you're adding up from the beginning. T1 is obviously the first term, and D is the common difference. It's this Tn here, and you need to remember that T sub n is the value of the last term. And I explained that on Friday by saying, if you're finding S10, for example, then the n in this formula becomes 10. So every place there's an n in the formula, you're going to put the number 10. S10 would be n over 2, which would be 10 over 2, times T1 plus T10. But since you're adding up 10 terms, T10 is the last term. Okay. The only other thing I want to mention here, let me go back to the beginning. The only other thing I want to mention about working with these formulas is sometimes you may not know the number of terms you're adding. So for example, when we take a look at question 1 right out of the gate, doesn't matter which formula you use, you're going to have to determine the number of terms. And in order to determine the number of terms, say in question 1b, you can still use the general term formula. And this is something you should be very proficient at, which means very good and accurate in working with. That you should be able to say Tn is 7 plus n minus 1 times, well, 7. The sequence or series in part B happens to have a first term of 7 and a common difference of 7. Hopefully you haven't forgotten everything over the weekend. That should be pretty obvious, isn't it? Okay, so we could simplify this by writing Tn equals 7 plus 7n minus 7, just by expanding this through, and you end up with Tn equals 7n. So in order for you to find out how many terms there are so that you can find the sum, and by the way, I would use this formula whenever possible because I just think it's simpler than the other formula. Okay. In order to find the number of terms, we go back to this idea of looking at a table where if I have a value of 98 for a term value, I'm trying to find n. So I would put 98 in for Tn. It's a pretty simple example. Divide 98 by 7. 14? Okay, good, thank you. Just warming up my brain here. It is 14. So now that you know n is 14, you're off and running and you can use that formula. Bottom line here, everybody, is you have a couple of different formulas that you can use for SN. Today what we're going to do is do that last example that we didn't quite get through on Friday. And a couple of you said you watched the video and it cut off after that second to last example. That's because we didn't finish the last example. So I'm just going to start off by asking, first of all, does anybody have any questions you'd like me to go over? All right, so let's go back to this question from the previous lesson. And I'm going to run through this fairly quickly. Not so quickly that you can't keep up and copy it down, but if you weren't here Friday, you're going to have to copy down what I have. If you were here Friday, correct me if I'm wrong, I think we got to B, or partway through B. Is that right? Okay. So that's not the question, by the way. This is the question. And this is on page, thank you, 10 of your unit handout. So this is the final example from last week. Briefly, I'm not going to spend time reading through this with you, but briefly what happens is you have an athlete who starts in this point, and they are 8 meters away from the first pylon. And the second pylon is 5 meters further down the line, and the third pylon is 5 meters further down the line. I'm not going to have enough room to draw this, but it goes all the way up to, these are your pylons, goes all the way up to pylon 10. And what happens is the athlete runs to pylon 1 and back. And then the athlete runs to pylon 2 and then back. And then the athlete runs to pylon 3 and then back. And the athlete has to do that to all 10 pylons. And you're told in this question that the distances to the pylon and back form an arithmetic series. Specifically, n is the pylon number. Pylon is just one of those cones. You know what I'm talking about, right? Just kind of a fluorescent orange cone or some kind of marker on the floor. And Tn is the distance there and back. And when I say there and back, I mean to that pylon and back. And what we did on Friday was we said, well, if the athlete has to run from where they start to pylon 1 and back, then the distance there and back is 16 meters. Pretty easy, 8 plus 8. In order for the athlete now to go from the start to the first pylon, or to the second pylon rather, and back, they have to run 8 and 5 is 13 to the second pylon and another 13 back. That's 26. And, you know, it isn't a really difficult thing to understand that each time the athlete runs to the next pylon and back, they're running an additional 10 meters because they have to run that extra 5 meters to the pylon and back. That's 10. And this is going to continue. We can do a third one. This will be 36. It'll be 8 plus 5 plus 5 plus 5 plus 5 plus 8. You're going to get 36. And this is going to continue until the athlete, and we don't know what that is, and I don't know that we want to find out what it is. We'll see. But this continues until the athlete has completed all 10 round trips. And here's the first question. What's the difference between Tn and Sn? Well, Tn is the distance there and back to pylon n. Okay, so if you know n is 5 and you calculate T5, you're finding the distance there and back to the fifth pylon. You're finding the distance to the fifth pylon and back. Sn, on the other hand, we said is the total distance. Total, I'm going to use the word cumulative. There and back to n pylons. And the key word there is S. Not because S stands for some, but because there's multiple pylons. You're going to the first and back, second and back. You're adding them together. It's not just there and back for one, it's there and back in total. You're then asked to find an expression for Tn. Well, that's easy. I just did an example like this with question 1b, where we looked at the sequence, and you can look at your sequence here and see that T1 is 16 and D is 10. Does that clock in your head? The first term is 16 and the common difference is 10. So we're going to load those into this formula and get T sub n equals 16 plus n minus 1 times 10. You just multiply that 10 through. I would say we probably multiplied that d through 20 times in this course so far. Just in the course of the last 4 or 5 days of classes, we keep coming back to that. The 16 minus 10 can be simplified to get T sub n equals 6 plus 10n. I'm not going to explain the meaning of this in words. If this were an assignment or a written response on an exam, you could put it into words. But the meaning of that is when you put a value of n in, you'll be finding how far there and back to that pylon. So if I put 10 in, 10 is an easy number to work with. 6 plus 10 times 10, 10 times 10 is 100. Plus the 6 is 106. It's 106 meters to the 10th pylon and back. That's all it means. Okay. Now, C is something we have not done before. What we want to find here, and I'm going to actually explain the meaning of it first. What we want to find is an equation, a single equation that I could put n in, and it would calculate the total distance to n pylons and back. And we're going to do the same thing that we did here. What did I do here? Well, I had two parameters. One of the parameters was T1, and I loaded the first term in there. The second parameter is D, and I loaded 10 in there. Well, let's do the same thing with our sum formula. So T1 is 16, D is 10. I'm going to put 16 every place there's an N. Sorry, I'm going to put 16 every place there's a T1. I don't know N. This is the whole point. Just like over here, a general term doesn't have N. That's too specific. And for D, I'm going to put 10, and we're going to simplify that. And I forgot, somebody see what I forgot there? What is it, Jay? Right, it's 2 times 16. I'll just put that 2 in a different color so your attention will be drawn to it. It should be 2 times that. I'm going to simplify this. Sn equals n over 2, and then I have, let's see, 32 plus 10n minus 10 You know, there's going to have to come a time, everybody, where I stop drawing those arrows at this level. Like when you see n minus 1 times 10, your brain should be able to cope with that and just say, well, it's 10n minus 10. 32 minus 10 is 22. Plus 10n. I don't want to get too caught up today in algebra, okay? But I'm going to multiply that n over 2 into this binomial. So I'm going to have n over 2 times 22. And when you have n over 2, which is a fraction, times 22, well, I guess I have to kind of talk about the algebra here. Look at how I wrote that 22 beside the n over 2, right here that I'm pointing at on the right-hand side of the screen. I did not, and you know that dot means times, right? I did not write it this way. And the reason is 22 can be thought of as a fraction. And we're going to be doing a lot of work in this course dealing with fractions in terms of things called rational expressions. They're algebraic fractions. And we want to be able to see this 22 as a fraction. One of the rules that we will review in that unit on rational expressions is when you multiply two fractions, you can always cancel common factors on the top somewhere with the bottom somewhere. So 2 divides into 22 and 2 divides into 1, which means, and this is fine for now, but when we get to rational expressions, I'm going to say stop doing this. Slash, slash kind of thing. With simple numbers, it's okay. But the bottom line is, when I multiply that out, I get Sn equals 11n, because 22 divided by 2 is 11. And I can use the same reasoning here. 10 divided by 2 is 5, and I get an n times an n, which is n squared. So that's a formula for Sn. What does it mean? It means the same kind of thing that the formula for Tn meant. But I'm going to put my Tn formula up here. 22 plus 10n, 6 plus 10n. The difference here, and I'm just going to explain this symbolically by using an example. If I put n equals 10 in here, what comes out? What did we say, 106? But that's Tn. It's the distance to the 10th pylon and back. If I put, for example, in this other one, n equals 10, I have to put it in two places, by the way. Get your calculator or your brain going and work out what we're going to get when we put n equals 10 in there. I want to say 610, because I'm just looking at this saying 10 squared is 100, times 5 is 500. Okay, I just put that on the shelf somewhere, 500, 500, I remembered that. 11 times 10 is 110. 500 plus 110 is 610. Now, you can certainly use your calculator, but my point is what we have found is S10. Yeah. What did I write? Oh, 660. 610, right? Okay, thank you, Aoki. The point is S10 is 610. 610? Okay. So when we put n equals 10 into the general term formula, we're just finding out to the 10th pylon and back. When we put n equals 10 into the Sn formula, we're finding out the total distance there and back to all 10 pylons. And I decided to use that as an example because then we have answered question C. It's 610, right? So I just saved a couple of minutes by kind of morphing C and D together, or B and C. Do you have two C's? Yeah? Okay, I'll fix that for next time. All right, now we're going to move on. And this is on page 11 of your unit handout. I guess what I would tell you is we're not really learning anything new in this lesson. What we're doing in this lesson is getting lots of practice working with math in applying it to these formulas that we now know for sequences and series for arithmetic. So I don't know, you could read through all of these specific things. I don't think it's really that important. It's more for my organizational purposes. Let's take a look at some examples. Determine the value of the first term for this series described below. Ultimately, what this boils down to is a test of your mathematical skills. Because what we have is an itemized list. We have the common difference, we have the sum of a certain number of terms, and the number of terms happens to be 13. And what you are asked to find from that is T1. So what your job becomes right out of the gate is there a formula we can use to find T1? Listen very carefully. And I may have said this to you before in some other questions. At this level, by the time you get to 20-1, and probably even 10C, but not as much, it's not helpful for you to approach math problems as puzzles. As you're going to sit here and go, okay, the common difference is -6, and I'm adding 13 terms. What might the first term be so that I can get a total of 4992? I mean, I don't know anybody who can think that way, but even if you could, you don't want to think that way, because then for every question, you have a new puzzle. What you want to do is use algebra. So is there a formula that we have that contains D, Sn, N, and T1? Yeah. It's that longish formula that we learned, Sn equals N over 2 times 2 times T1 plus N minus 1 times D. And forget for a second that I know many of you can answer this question. That's not the point. I'm going to take almost every opportunity in this course to help you develop your math skills to a higher level. And that's how I teach math. There's content, but we're learning math around that content. We know N is 13. Every place there is an N in this formula, 13 is going to go in. We know D is -6. So every place there's a D, we're going to put -6. And we know Sn is 4992. And my point is there's only one thing in that equation we don't know the value of, and that's T1. So it's possible to solve for T1. When I put these numbers in and I have 4992 equals 13 over 2 times 2 times T1 plus, and I so much want to just write 12 there, where these N minus 1 is. I'm not going to, because I know there'll be one or two people who go, where did the 12 come from? But I'll put 13 minus 1, and then -6, and again, that -6 is in brackets. So how do you solve an equation? What I'm going to talk about now is not for this equation, but for all equations. Your first step is to simplify, and what I mean by that is write things simpler than they are written. 13 minus 1. Simpler to write 12, isn't it? And 12 times -6, which is, I think, is -72, that's a lot simpler than any of this stuff, even though it's a negative number. So now what I have is 4992. Now, I know that some of you will want to divide 13 by 2, and that's fine. You certainly can, and I'll talk about doing it that way later. But I'm not going to. I want to stick with fractions. I end up with 2T1 minus 72. I'm going to do one more step with you, and then I'm going to explain a general procedure for solving equations. It doesn't really fall under the classification of simplification, but we would much rather not work with fractions. And what I mean by, I don't mean let's take 13 divided by 2 and have decimals. I don't want that. I mean in any equation, whenever you have fractions, you want to do what you can to get rid of the fractions. So what we can do here is multiply both sides of the equation by 2. You've learned as a general principle in math that when you have an equation, you can perform the same operation to both sides, and that keeps things in balance. So what happens on the left is I get 4992 times 2, which is 9,984. Thank you. Can we just double check that? You double check it? Okay, good. Now, again, you just have to deal with it. This is the kind of teacher I am. I'm not just going to solve this and show you how to solve it. I need to explain some things to you. When I multiply the right-hand side by 2, what happens is that the 2's cancel, okay? And I'm left with 13. I'm left with 13 times 2t1 minus 72. And it's at this point in time that there's probably at least 2 or 3 of you that are wondering this. And people never really ask until later. They go, oh, if you go back to that question, how come? And they ask it. How come I didn't multiply the 2t minus 72 by 2? And that's a great question. The answer is I don't. And the reason is when I multiply, I don't distribute. If I asked you to find 2 times 3 times 4, would you look at that for a second and confirm that it's 24? Okay. So how can I get 24? I can go 2 times 3, which is 6, times 4 is 24. I can go 2 times 4, which is 8, times 3, which is 24. I can go 3 times 4, which is 12, times 2, which is 24. What I do not do when I'm multiplying things is that. I don't do that. I don't go 2 times 3 is 6, 2 times 4 is 8, 8 times 6 is 48. I do that when there's a plus in between. And in here, there's a times. So as long as I multiply either the 13 or the 2t minus 72 by 2, then I'm golden. There's nothing wrong with that. Okay, now I'm going to give you a general analogy, and it helps some people. Other people, you won't need it, but we're trying to unwrap this thing to get at T1. So imagine that I give you a Christmas present. Next year you come to my room, last day of class before Christmas, I say, Merry Christmas, I give you a present. And I've wrapped it in a very meticulous way. What I've done is I've put tissue paper around it. Then I put it in a box. Then I've wrapped the box with paper, and then I put a bow on the box. Okay? And I want to write this down so you can look at it. I've put tissue paper. I've wrapped it in tissue paper. I put it in a box. I've wrapped the box in paper. I put a bow on it. Are you with me on that? But we're math people. We're not excited little children. We don't tear the thing open with no regard for rules. If I say to you, you have to get at what's inside, and you have to do it in a organized, methodical manner, then whatever I did last, you have to undo first. Doesn't that make sense? You can't take the tissue paper off of the present until you have removed it from the box. And you can't do that until you've taken the paper off of the box, and you can't do that until you take the bow off. So what you would do first is you would take the bow off. You would start at the bottom of the list, and you would do the opposite of what's there. You take the bow off, then you unwrap the box, then you take it out of the box, then you remove the tissue paper. And what I'm getting at is when you're rearranging an equation, it's bed mass in reverse. What is the first thing that's done to T1 here? The first thing is it's multiplied by 2. That has to be the last thing that you take care of when you unwrap it. So writing this down, we have multiplied by 2, then we have subtracted 72, then we have multiplied by 13 to get that 4984. So in order for me to solve for T1, I have to start with that 4984, undo the times 13, which means I divide by 13. That's my first step. I take 9984 and I divide by 13. Couldn't tell you. $768. And I'm left with 2T1 minus 72. Well, I can't divide by 2 yet because 2, multiplying by 2, is the very first thing that happens to T1. It's got to be the last thing I undo. I've undone this. Now I have to undo the minus 72. That's why at this point you add 72 to both sides. And let me be crystal clear on something. You certainly are not going to write this every time you solve an equation. I'm trying to explain to you that as...
Kira Little Poplar to Student Services, please. Kira Little Poplar to Student Services.
I'm trying to explain to you that as the equations get more complicated, sometimes you might have to resort to this analogy, remembering that the first thing that happened to your unknown is the last thing you take care of in unwrapping it. So now what do we get? We get 750. Is my math right there? Or is it 740? $840. Wasn't even close. Is 840 correct? Okay. Equal, now we're in familiar territory. Now I can divide both sides by 2 and I get T1 equals 420. So the first term is 420. The bottom line is this equation at the top of the screen in green is something that I would expect that you can rearrange and solve for T1. Determine a general expression for the sum of n terms in this series. This is exactly the same as the first part C in the last example of the lesson that we finished off today. You know the first term is 3. You know the common difference is 6. Am I right? So we can put those two parameters into my general term formula for the sum. Not my general term formula for a term, but for the sum. N over 2, 2t1 plus n minus 1 times d. And I just realized something. A number of you were away on Friday. Friday was the day I gave the formula sheet out. I will get it to you today. Sn equals n over 2. 2 times t1, which is 3, plus n minus 1 times 6. Again, simplify things first. 2 times 3 is 6. 6 times n is 6n. 6 times negative 1 is negative 6. Oh, fortune is smiling on us in this example because I have in brackets 6 minus 6, which I don't even need to worry about because it's 0. I get Sn equals n over 2 times 6n n times n is n squared. 6 divided by 2 is 3. It's hard to believe. I find it hard to believe. 3n squared. Here is our series. 3 plus 9 plus 15 plus 21. Is that it? Okay. Yep. I'm actually kind of amazed by this, and I'm serious. This is used to find the sum of any number of terms. If I put 1 in here, I get 3 times 1 squared, which is 3. Yeah? Work out what you get when you put 2 in here. 12, right? Aren't we supposed to get 9? No, we're supposed to get 12 because 3 plus 9 is 12. If I put 3 in here, 3 times 3 squared. 3 squared is 9. 9 times 3 is 27. I'm actually kind of amazed by this. If you add up the first 3 terms, you get 27. I mean, I know it should work, and I shouldn't be amazed because the algebra never lies, but it's kind of interesting, I think. Let's try another one. I'm going to write this down and just say a couple of words about it, and I'm going to let you stew on this for a minute. This question says, when you add up the first 7 terms in a series, you get 114. And when you add up the first 8 terms, you get 120. And the question says, what is the value of the 8th term? So I'm going to let you stew on this a bit. And when you get the answer, put your hand up and then down so I know that you get the answer. The hint I would give you is you should not need a formula and you should not need a calculator. I mean, there probably is a way to do it with a formula and a system of equations. Nate, you have it? Is it a number less than 10? No? Then it's not right. Not that that's a really helpful hint. I didn't want to hear your answer. It's definitely a number less than 10. What is it?
6.
It's 6. Listen, 114 is what you get if you take the first term plus the second term plus the third term plus the fourth term plus the 5th term, plus the 6th term, plus the 7th term. $120 is what you get when you add those 8 terms together. Why is S8 bigger than S7? Well, because it's adding more terms, isn't it? How many extra terms is it adding? Just that one extra term, just that 8th extra term. The difference between these two numbers, if I subtract that, 120 minus 114 is 6. And if I take T1 plus T2 plus T3 plus T4 plus T5 plus T6 plus T7 plus T8, and I subtract T1 and T2 and T3 and T4 and T5 and T6 and T7, all I'm left with is T8. And you're going to see this question crop up time and time again in the remainder of the unit, because it's one that you need to see frequently in order to make sure that you get it on an exam. Let's take a look at number 4. The sum of the first two terms of an arithmetic series is 13. The sum of the first 4 terms is 46. And then the question says, what are the first 6 terms and what's the sum of the first 6 terms? Ultimately, these are the 2 things you need to crack the case wide open. If you know the first term and you know the common difference, then you ought to be able to find out anything. Well, we have this formula. And it turns out we have done a question very similar to this before, but we did it with a different formula. These are missing parameters. And I honestly don't expect anybody to remember, because I've only talked about it once or twice. But I guarantee if I ask this question to my Math 30s or to you at the end of the semester, you will all know. How do you find missing parameters? Liberty. You make the 2 separate equations. And in a more general sense, because sometimes we don't need 2, but if we have 2 missing parameters, we make those equations by loading in a pair of numbers that makes the equation true. So for example, when it says the sum of the first 2 terms is 13, that means when I put 2 in for n in that formula, I get 13 for Sn. And I will have a formula that's missing a T1 and missing a D. But I'm also told I thought I changed it, I guess not. You're also told, there we go, that the sum of the first 4 terms is 46, which means when I put 4 in for n, I have to get 46. And each of those replacements of that ordered pair, it's not an x and a y, but we can still call it an ordered pair because the order of the numbers matters in the table, and it's a pair, will give me a different equation. So if I put, we'll start off with the 46. I put the 46 here. I have to put the 4 here. And I am going to take the liberty here of challenging you to say if I put 4 in for n, n minus 1 is 3. I mean, do we really need to write 4 minus 1 and then change it to 3? I'm just going to do that. There is an equation that contains T1 and D. If I do the same thing here, well, you know what? Let's clean this up first. Let's multiply both sides. Let's multiply both sides by 2, making this 92 equals 4 times 2t1 plus 3d. Can I divide 92 by 4? Does that work without a decimal? Because if it does, that would be really nice. 23. So I end up with this kind of tidy equation. 23 equals 2t1 plus 3d. Let's just put a box around that. Now what I'm going to do is the exact same thing for 2 and 13. Which would give me Sn is 13 equals 2 over 2. Well, that's nice, isn't it? 2 over 2. You're not gifted that very often in a math problem. And then 2t1 plus 3d. Whoops. Whoa, 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 whoa. Not plus 3d, plus 1d. Because I'm putting into this formula at the top of the screen for my second equation, I'm putting 2 there. I'm going to clean that up just a little bit and write 13 equals 2t1 plus d, because 2 over 2 is just 1. There's my second equation. Can somebody tell me what we can do to those two equations? It's a system of equations, and that's what Liberty meant. We now have two formulas or two equations that we can use. What can I do to those two equations to get rid of the t1s? I can subtract them. And I want to rewrite these just to illustrate a point. 23 equals 2t1 plus 3d, and 13 equals 2t1 plus d. I think I've mentioned this to you before, but I'll find out. Have I mentioned the fact that I don't really like subtracting, that addition is easier? So you can either subtract them, and if you do, that's fine. There's nothing wrong with this. 23 minus 13 is 10. 2t1 minus 2t1 is nothing. 3d minus d is 2d. I would, though, multiply everything in this equation by -1 and add it. It doesn't matter, but as things get more complicated, it might be easier. Bottom line, now I know d. d is 5. The common difference is 5. We've almost cracked the case wide open. We know the common difference. But I still need to know the first term. Anybody, how can I find the first term now at this point in time? Yeah, you finish it off. Sure, it's just algebra. Put it back into one of the formulas. It doesn't matter which one. I'm going to use this bottom one here because it's just sitting right there and I got some room. 13 equals 2t1 plus 5. This should be child's play. Take 13 and subtract 5 and then divide the result by 2. And I want to say that you get t1 equals 4. Do you get 4? Okay. Now you know everything. Does this question say find the first 6 terms and the sum of the first 6 terms? Okay. Well, at some point, you have to say, geez, do I have to use a formula for this? I mean, what are the first 6 terms? The first term's 4, the common difference is 5. Just keep adding 5 and you'll have the terms. Need one more, I guess? Are we in agreement? And you know, I would even go so far as to say if you want to find S6, why do you need to use a formula to find S6 to add those 6 numbers together? I want to say 99, but I could be wrong. It is 99? So these are the first 6 terms, and S6 happens to be 99. The math is in the problem solving. Where you go from there and how you get S6 equals 99 is entirely up to you. Second and the fifth term of an arithmetic series are 8 and 29. What's the sum of the first 15 terms? Well, again, this is our goal. Now, it turns out that this problem, let me write out in a table what we're given. Let me ask you a question first of all. You're going to have to read the question carefully and think about this. What is this column? Is that Tn or is it Sn? Aoki? It is Tn. Because it says the second term is 8. This problem of going from this information in the table to to finding those two parameters is one we've done 4 times now as a class in examples. One of the times we did it as a system of equations, but the simple way to do it is this. Plus D, whoops, plus D, plus D, plus D. And in fact, I don't know. How many of you are capable of understanding that since we're going from the second to the fifth term, we're adding 3 common differences? Okay. You know, and I probably shouldn't write that there. I should probably be writing, I'm being nitpicky here, but I should probably be doing this. We're adding 3 to the term number, which means we add 3 common differences to the term values. Bottom line is 8 plus 3D has to give you 29. Can you do me a favor and solve that? I would like to say 7. So the common difference is 7. I really hope you appreciate and understand what I mean by knowing these 2 parameters breaks everything wide open. You can find anything. So now the question is, how can we find T1? Well, why don't you just subtract 7 from 8? I don't think you need to set up an equation for that, although you could. You could use the general term formula as a missing parameter with T1, but there we go. And now, I've mentioned this before too. This is my philosophy in math education. You take a problem that's complicated and you turn it into something you've already done. Well, you've already done this. We did that on Friday. If you know the first term in the common difference, what's the sum of the first 15 terms? S15 equals 15 over 2. I'm just using the formula. Times 2 times T1 plus 15 minus 1 times 7. And again, I hope you're getting more comfortable with me just writing 14 instead of 15 minus 1 whenever possible. So we work that out. Oh, that's easy, 750, I think. I better be careful. I said, oh, that's easy, and I might have it wrong, but let me do it again. No, it's 750. So the answer to this question is 750. But just before we go on and tackle the final few examples today, you know, you need to appreciate that this could be a numerical response question. There's a lot of work that needs to be done here to get to that answer. And some of you may be used to just sitting and looking at a multiple choice or a numerical response question and going, oh, yeah, I know what to do, and plunking away on your calculator. I don't think that's likely to happen here. So if you're the kind of person who up until now has kind of been skating a little bit and just looking at stuff and it's obvious, that obviousness is going to start to fade for many of you. All right, what's the sum of the first 12 terms? Well, first of all, this is pronounced 2 root 3. How do we pronounce this? Well, we pronounce this 2x, right? If I had this sequence, I hope it's obvious what the common difference is. Would you say the common difference is 3? Oh, Thanks for keeping me on my toes. 8. 2, 5, 8. Yeah, of course. Would you agree the common difference here is 3? Okay. What if I had... what's the common difference here? Boy, my brain just does not want to write an 8 today. What's the common difference here? Go ahead. 3x. And what that literally means, we don't often talk about this, but this first term is that. It's 2 x's. And the second term is that. And the third term is that. 2x means 2 x's. It doesn't mean x times x, by the way. It just means there's an x and an x. It's x plus x. So what is the common difference here? Aoki, do you know? Josh?
Is it 2 root 3?
Not 2 root 3. 3 root 3. Right? Because what we're doing here, this first term is this. It means 2 times the square root of 3. It means 2 root 3's. It's root 3 plus root 3. My next term, well, it's plus, so I guess I can put pluses instead of commas, but it doesn't really matter. My next term, which is this, is the following. I'm adding 3 of those things. If I went from 2 cats to 5 cats, I've added 3 cats. Would you agree? If I go from 2 to 5, I've added 3. If I go from 2x to 5x, I've added 3x. If I go from 2 root 3 to 5 root 3, I've added 3 root 3. So the first term here, this is all just me explaining, so I'm going to erase it all. The first term is 2 root 3. The common difference is 3 root 3. So what's the sum of the first 12 terms? Well, I'm going to go to our formula again. I'll write it down this time. And we load in those 2 parameters. So every place I want to find the sum of the first 12 terms. So every place I see an n, I put 12. Every place I see a T1, I put 2 root 3. I put 12 in for n. That gives me 11 times the common difference is 3 root 3. Okay. Let's use another analogy here. If I had... No, I'm not even going to go that far. I am multiplying here 11 times 3 times root 3. 11 times 3 is 33. So I've got 33 times root 3. I've got 33 root 3. I've got 2 times 2, which is 4. I have 4 root 3. And 12 divided by 2 is 6. Would like everybody to ponder, please, for me. What is it we get if I take 4 root 3 and I add 33 root 3? You're not going to enter it on your calculator and get decimals. That's not what I'm after. Jay? 37 root 3. You know, if I have 4 kittens and I add 33 kittens, what do I get? Other than immense joy, I get 37 kittens. and then times 6, well, I can multiply the 6 by the 37. Like imagine me writing 37 root 3s. Root 3, root 3, root 3. I write 37 of them, and I take that 37 and I multiply by 6. I'm going to have 6 times as many. 222? Yeah? Root 3s. And this is the first illustration in this course where even though the answer is a number, you can't do this on your calculator. And we're going to talk about why later on in the course. Okay. What's the first term? The first term is 3x plus 2. What's the common difference? What am I adding to the first term to get the second term? What am I adding to the second term to get the third term? Do you know? X plus 1, sure. I'm adding x because the 3x turns to 4x, which turns to 5x. And I'm adding 1 because the 2 turns to 3, turns to 4. I mentioned at the beginning of this that many of these examples today are about building math skills. They're not directly about sequences and series. So how do I find S? Was it S12? How do I find S12? I put 12 over 2. Then I go 2 times T1 plus 12 minus 1 times the common difference. I just load everything into this formula. 12 goes here. 12 goes here, but I'm subtracting 1. The common difference is x plus 1. The first term is 3x plus 2. So at this point in time, everybody, this is now just turned into an algebra problem. This is probably a grade 9, maybe a grade 10 question where your teacher just throws this out there and says, what does this equal? Simplify it. Well, is there a simpler way to write 12 over 2? Without a doubt. Is there a simpler way to write 2 times 3x plus 4? Yes. Sorry, 2 times 3x plus 2. Yep, 6x plus 4. How did I get 6x plus 4? Just expanded it out. Okay, good. I take that 2 times the 3x. I take the 2 times the 2. Do the same thing here and get 11x plus 11. Is there a simpler way to write what's in brackets? Well, yeah. Instead of writing 6x plus 11x, you can write 17x. Instead of writing 4 plus 11, you can write 15. I've been on autopilot here for the past minute or two. Those numbers look okay? Do you know what I mean by autopilot? Sometimes I just get going and I'm not even thinking about it. Now we can multiply that 6 through. There's going to come a time where we'll make an argument that it's almost better to leave the 6 there. But for today, we'll multiply it through. I think 102x plus 90. Briefly here, I could easily make this a numerical response question on an exam. I could give you the question and say S12 equals 102x plus a. What is the value of a? Numerical response. And you have to do all this to find out a is 90, and then you enter 90. I think we have one more. Is that right? Okay. This is one, I don't know that anybody could get it without a little bit of help from me, but this is one that is not that difficult in terms of the algebra on paper. There's not much work. It's actually quite simple if you understand it. You remember back in earlier examples where we found an expression for Sn, and I said if you put n in, that tells you the total up to that point. Let's do that. Let's start creating a table. N equals 1, 2, 3. Let's just go up to here. Sn. So I would like you to put, each and every one of you, use your calculator or your brain, put 1 in for n and calculate what Sn is. Seven? I mean, when I put 1 into an expression for n, any place there's an n, those n's kind of just go away, don't they? They become 1s. So I get 2 plus 5, which is 7. Let me ask you a question. Can anybody tell me what the first term is in the sequence and why? Jay? It's 7. Why? And this is difficult to put into words.
Because if Sn is the total of terms and there's only one term, then that means
Sn is the total of the terms up to n, and there's only one term, so the first term must be 7. If I gave you the first term and I said the first term is 7, what's the total of the first term, which doesn't quite sound right? The answer is 7. We know the first term. That's pretty valuable. Can you put into this Sn formula 2 and calculate what we would get? So what we've done here, I'll show it. We've done that, and that gives us 7. Now we're doing this. So every place we see an n, we put n. 18. Somebody, what's the second term? Put your hand up and down if you think you have it. Paige, do you know? It is 11. What's the reasoning for that?
I did 18 minus 7 because of the first term is 7, and the total of the 2 would be 18.
Right. So if I start listing the terms, the first term we already know is 7. We know that this has to give 18 because the sum of the first two terms is 18. So if we take 18 minus 7, you get 11. Now, at this point in time, if you're told it's arithmetic and you are, wait a minute, is the common difference 11 or is the common difference 4? It's 4, right? We look at the terms. If that's true, this should be 15, shouldn't it? Adding 4. This should be 19. Okay, wait. S3 should be 7 plus 11 plus 15. Is that 33? S4 should be the sum of these 4, which I believe is 52. But check it out. And this is the part that amazes me. I don't know why. I'm just easily amazed, I guess. That if you put 3 in here, you have to get 33, and you do. And if you put 4 in there, you have to get 52, and you do. So, by the way, to determine the next term, let's add 4 again. 4, 4, 4, yeah. And by the way, if you're told it's arithmetic, you can stop here. As soon as you know these two terms, you're off and running, because then you know the common difference. You can just keep adding it. And I guarantee you on your exam, and I don't know when your exam will be, it will be next week, probably near the end of the week. On your exam in this unit, there will be a question that gives you a formula for Sn, numerical response, and says, what's the 6th term? And when you put 6 in there, that's not going to be the 6th term. You have to put 6 in there and put 5 in there and then subtract the two sums. Or do what we did and just continue building the table. We are done now with arithmetic patterns. Starting tomorrow, we're going to look at geometric, which is totally different. Geometric occurs when you multiply by something each time instead of adding. So today is our last shot at working on these problems. There are some textbook questions and then a couple questions that I've typed out for you. Not last shot like ever, but tomorrow we move on. Okay? So get to work on those. I have to just do something quickly at my computer and then I will be around to help you.